What's up, guys? It's Mr. Brengle, and today we're going to be going over the math for the energy unit. And I'll go ahead and apologize up front. It's really windy outside, and I'm right by a window here, so if you're hearing some static or wind sound, that is why. So let's first talk about equations here. So first equation is for gravitational potential energy right here. Okay, gravitational potential energy. Sometimes you'll see that written as GPE, but a lot of times it'll just be E with the subscript little g. That is going to be equal to the object's mass times the acceleration due to gravity, or the gravitational field strength. That's always going to be 10 meters per second squared, times the object's height. So its vertical location above some defined point as what 0 is. And I'll explain that here on like the second problem. Second equation here is for kinetic energy. I think that one is pretty obvious with the K right there. And that is equal to 1/2 times the object's mass times the velocity squared. And I want to be clear here, this is just squaring the velocity. It is not squaring the m, the mass, either. So if this parentheses was over here and was around mass and velocity, and then it was squared on the outside, then we would be squaring both. But when it's just written with no parentheses, it's only squaring the variable that it's connected to, which is the velocity. And then our elastic energy is a very similar equation, 1/2 kx squared, which I believe we've seen before. So now the K is the spring constant. Okay, spring constant is a known value that will be given to you in the problem. You won't be able to know that on your own, and it will change depending on the material, so, or what type of spring it is. So and then X is your stretch or compression, whether that's with a spring or a bouncy ball or whatever, scrunchy, how far it was stretched from its equilibrium position or how far it was compressed from its equilibrium position. And then the last two here would be work. So you won't actually see a lot of calculations for this in what we do today, but we do have something else that we would use the work equations for. I definitely want you to see these and understand these, though. We talked about this a little bit in the intro videos, but work is equal to change in energy. Okay, so that's what that red equation is down here. Work is equal to change in energy. So the work that you put into something is equal to the amount of energy that you had to use to do that, right? And we demonstrated that in our intro video where I had all the virtual labs up, and we kind of talked about that. So, and then if you're just trying to calculate work, like let's say you don't have enough to calculate the change in energy, work is the force that was applied to something times the distance that force was applied for. So if I, pick up my calculator and I lift it up above the desk, well, I've done work to that calculator. It has now gained gravitational potential energy. And the gravitational potential energy that it has gained is equal to the amount of work that I did on the calculator. So I applied a force to it and I raised it up some distance. When you multiply those together, that's equal to the work, which is equal to the change in energy, which would, in this case, be gravitational potential energy. Okay, so just a little brief synopsis there. Let's go ahead and look at the first couple problems here. So we're going to do this in two parts. I'm going to do 1 through 5 with you first, and then I'll have separate videos for 6 and 7. So this first problem, it says, how much kinetic energy does a 2,000 kilogram SUV traveling 70 miles per hour have? Okay, so it's 2,000 kilograms, it's moving 70 miles per hour, and it does give us a conversion here because we will want to convert this. Okay, so the first step here would be to do that conversion. It's tough to deal with miles per hour. We typically do meters per second, so let's convert it to meters per second. I like to do it like this. I'm going to put 70 miles over 1 hour. Then we're going to set up a little table here, and we're going to cross cancel. So it does tell us that 1 mile is equal to 1,600 meters. That was over here. So when we do this, it will cancel out the miles. we'll be left with meters per hour. So now let's get rid of hours. 1 hour, see now these will cancel here. 1 hour is equal to 3,600 seconds. So you could have done that in 2 steps. You could have gone from hours to minutes and minutes to seconds, or you can just know that there's 3,600 seconds in an hour, which is not a bad thing to learn anyway. And this is going to come out to be 31.11 meters per second. Okay, so we need that in order to do this problem, because remember, kinetic energy, so if we're going to actually solve this, kinetic energy is equal to 1/2 times the mass times the velocity squared. So do 1/2 times the mass, which it told us was 2,000 kilograms, times the velocity squared, which is 31.11 meters per second squared. Okay, so when you do the 31.11 squared, that should come out to be 967.83. And then you're going to multiply that by 2,000, and then divide it by 2, and you are going to get EK, our kinetic energy, is equal to 967,832. And then the units here are what we refer to as joules. Get in your, I guess the one positive about this is I don't have to hear you guys snicker about joules in class. This is spelled Joule, a joule. Okay? And that's how you measure energy and work. Okay, so we will always have joules. If it's any type of energy or work, you will measure it in joules. Okay, number 2. Okay, so this is the one I was talking about with the like setting a reference point that we define to be 0 meters. So basically it says, consider the physics binder resting on the table. It's 3 kilograms. Determine the gravitational potential energy of the Earth book system if the 0 reference level is chosen to be. And then we have 3 options. We have the table, the floor, and the ceiling. So what that's saying is, for the first example, it's saying that this level right here is 0 meters. That's for the first one. Okay, so I'm going to put that there, and we're looking at where is this book, and just imagine that the book is sitting on the table like this. Okay, don't get confused. But this level right here is 0 meters. So obviously the book is on the 0 reference level. Okay, so if you had to guess, what's the gravitational potential energy going to be? Well, it should be 0 because the object has no height. Okay, so remember that Eg is equal to the mass of the object, which is 3 kilograms, times the acceleration due to gravity, which is 10 meters per second squared, times the object's height, which in this case is 0 meters. So it doesn't matter what the mass and the gravitational potential energy are, since the height is 0. That means that there is no gravitational potential energy. Okay, so I'm not even going to do the calculation. We just know straight up, okay, that object is sitting, it can't fall, right? It can't go down any further to the 0 reference level, okay? Now, this is a little bit different from if we choose the 0 reference level to be the floor, okay? So I'm going to do that now. So we're now saying that down here, this is 0 meters, okay? And now the book could fall from the table down to the floor. So it does have some gravitational potential energy, okay? So we're actually going to do this equation here. So gravitational potential energy is equal to mass times acceleration due to gravity times the height. So we'll go ahead and plug that in. 3 kilograms times 10 meters per second squared times the height of the book, which in this case, it is 0.68 meters above the floor. So I'm going to make this a positive displacement. Okay. And then when you multiply 3 times 10, it should be 30 times 0.68 is going to give you 20.4 joules. Okay, 20.4 joules. So that's how much gravitational potential energy is stored up in that book. So if it were to fall, theoretically, all of that gravitational potential energy would be transferred into kinetic energy by the time it hits the floor. Okay, last one here, then another situation. We are going to be now changing the zero reference level to be the ceiling. So I'm going to kind of, just draw it roughly up here. So this is the ceiling and this is 0 meters. So now the book is below the zero reference level, right? So it could theoretically return to the zero reference level if someone were to throw it up. So the point of this is that our displacement this time, since the book is below the ceiling, is going to have to be negative. Okay, so you can have negative displacement, we know that. You can also have negative energy. Okay, so mass times acceleration due to gravity times height. Same calculation, just slight modification in the number. So 3 kilograms times 10 meters per second squared times negative 2.5 meters. Okay, so when you do this, it is going to give you negative 75 joules of energy. Okay. All right, so you can see that changing the reference level, what we define to be 0 meters, certainly affects the energy, right? So just remember that the zero reference level is something that we set. So the first time it was on the table, that was 0. Then we set the zero reference level to the floor. Then we did it to the ceiling. Okay, so we can see how much energy that object, the book in this case, has in all three of those situations. Okay, so let's go ahead and then move on to our next couple problems here. So this one says a bungee cord stretches 25 meters and has a spring constant of 140 newtons per meter. How much energy is stored in the bungee? Okay, so it stretches 25 meters, has a spring constant of 140 newtons per meter. How much energy is what we're solving for? Okay, so this is clearly talking about something that is stretching and has elastic energy. Okay, so we are going to use our elastic energy equation. And that is the one that looks like this. Elastic energy is equal to 1/2 times the spring constant times the stretch or compression squared. Okay? So let's go ahead and fill that in. Elastic energy is equal to 1/2 times the spring constant, which is 140 newtons per meter. Remember, that's a measurement of how much force is stored up in a meter of that bungee cord. And we are multiplying that by the stretch squared, which is 25 meters squared. Please do not forget to square, because that is the number one mistake on these problems. These are not, this is not hard, right? Like it's a 2 variable equation. You're plugging in 2 numbers. The most errors are made right here, right here. Okay, you must square that 25. Okay, so 25 squared, then multiply it by 140, then cut it in half, and you are going to get an energy of 43,750 joules. Okay, 43,750 joules. Okay, so that's elastic energy in that bungee cord. Now let's do one that's about kinetic energy. So it says, how fast does a 50-gram arrow need to travel to have 40 joules of kinetic energy? Okay, so this one's a little bit different. It's actually given us the energy involved in the problem, and we are going to figure out how fast is this object traveling. Okay, so the first thing here is we need to convert 50 grams to 50 kilograms. So to do this, we're going to need to divide by 1,000. Okay, divide by 1,000. So we're going to move the decimal place over 3 times because there are 3 zeros in 1,000. Okay, so this is going to be equal to 0.05 kilograms. Okay, 0.05 kilograms. Now, let's go to our kinetic energy equation, 1/2 mv squared. We're going to be solving for the velocity, so we're going to go ahead and plug in everything else. 40 joules is equal to 1/2 times 0.05 kilograms times the velocity squared. Okay, so again, we got to be really careful with that squared. We are going to have to use a square root at some point. Okay, so if you go ahead and do 0.5 divided by 2, or 0.05 divided by 2, let's just get that out of there. 0.05 divided by 2, it's 0.025, okay? So this is 0.025. That's equal to 40 joules times v squared, okay? So we need to divide here by 0.025 to get that off of this side. We need to do it on the other side, 0.025. Okay. And then that is going to give us 1,600 is equal to v squared. At this point, it's where we need to do the square root on each side to get rid of the squared over here. So this and this cancel. We're left with just velocity on the right side, and that's equal to the square root of 1,600, which means that our velocity here is equal to 40 meters per second. Okay, 40 meters per second is the speed of the arrow. All right, now the last one here for this segment of the video. How much energy is stored when a railroad car spring is compressed 10 centimeters? And then it says the spring requires about 10,000 newtons to be compressed 3 centimeters. Okay, and it's again asking for how much energy. Okay, so this one is just a little bit tricky. The first thing is it gave us the compression delta x as 10 centimeters. Okay. Now, we want to convert this to meters. So, in order to do that, we've got to divide by 100. Okay. All right, so we're going to move the decimal place 2 to the left. So 10 centimeters is going to be equal to 0.1 meter. And that should make sense, right? Think about a meter stick, okay? 10 centimeters on a meter stick is 1/10 of the meter stick, right? Because there's 100 centimeters in a meter. So that's why it's 0.1 meters. 0.1 meters is 1/10, okay? Now, the next thing here is that it tells us that the spring requires 10,000 newtons to be compressed 3 centimeters. So once again, let's go from 3 centimeters to meters, which is going to be 0.03 meters. Okay, move the decimal to the left. Okay, now what could that possibly be? Well, if we look at our equations, let's go back and let's look at the first page here. Let's look at our equations. The only one that has a stretch or compression is the elastic energy equation, right? So let's go back to our problem here. Well, we're missing the K value, right? We're missing the spring constant. That's what it's given us. Remember that spring constant is measured in newtons per meter. Okay, so it gave us 10,000 newtons per 0.03 meters. Okay, so if you just go ahead and do that calculation, 10,000 divided by 0.03, it's going to give you 333,333.3 repeating. It's the most threes that you can possibly get. Okay, so now we have the stretch, We've got the spring constant. We can go ahead and solve for the elastic energy. 1/2 times kx squared. So we'll do 1/2 times our spring constant of 333,333.3 repeating, times the stretch, which is 0.1 meters, and then that is squared. Okay, so then we go ahead and do this. 333 times 1/2 times 0.1 squared comes out to be 1,667 joules, rounded. Okay, so those are some basic problems for energy. We got a little bit of, we did gravitational potential energy, we did some kinetic energy, we also did elastic energy. The next portion of this math is going to bring in those bar charts that we've talked about and looked at on concept builders and in the original notes. And we're going to add the math and the bar charts together in the next section.